Survival in the sea means many things. How can animals like this crab live part of their lives on land, part underwater? Pounds like this one collect enough food to survive. How can a jellyfish survive treatment by waves when it's so fragile it breaks in two when lifted into air? How can fish keep on moving tirelessly, always on the go, and keep it up for a fish's lifetime? These are some of the questions that have to do with survival in the sea, which is the general subject of this series. We start with animal adaptation.
Every animal is adapted to his own living conditions, a certain environment to which he is best suited. Some creatures, like man, are very versatile. They can adapt to a variety of conditions. For example, he is not a water creature, but here you see me living and breathing underwater. My accustomed element, air, is artificially supplied. Man is especially versatile because he can artificially control his environment. The word that describes the understanding of how animals fit into the area in which they live is ecology. The aim of ecology is to try to understand the relationship between the animals and the world they live in, the relationship between organism and environment. Now, most animals are much less versatile than man in this matter. Many of them are uniquely adapted to just one narrow, limited set of living conditions. They occupy what we call an ecological niche. I'm going to take you with me in a moment, underwater and along the shore, to explore some of the peculiar conditions of life imposed by the sea. We will observe how animals adapt to these environments. But first, let's answer the question about the crab. How can he live both in air and in water? Just like land animals, every underwater animal must breathe. They must have some means of passing water in quantities over a gill or some other part of the body that acts like a gill. The gill extracts the vital oxygen from the water and also gets rid of the carbon dioxide waste. Beneath the hard outer covering of the crab, on each side of the body, is a double-purpose gill. This is the apparatus that enables the crab to extract oxygen from both air and water. Water flows across the gill and out again here. When the crab is out of water, the gill must nevertheless be wet. Oxygen must be dissolved out of the air into the moisture on the gills. Thus, some kinds of crabs can breathe both in and out of water.
Here is the same kind of crab on his home grounds. He pumps so much water over his gills, you can see it forming a small fountain as it comes out. This pumping action must go on 24 hours a day, whatever else the crab may be doing at the same time. By way of extreme contrast, here are some microscopic animals. They are so simple in structure, they absorb oxygen all over their bodies, so they have no need for special breathing equipment such as the gills of the crab. To study the relationship of marine animals to their environment, sometimes it's helpful to get right into the environment with them, as I am about to do here. We're going to look at various ways animals adapt to their surroundings to carry out the vital functions of breathing, escaping enemies, and getting food.
Quite large marine animals, if they are relatively inactive, like the sponge, can also absorb oxygen directly without special breathing organs. The sponge pumps the life-giving, oxygen-bearing water through holes in its sides, forcing the water through a maze of tiny internal canals and chambers. After circulating throughout the sponge, the water comes out at the top. A few drops of ink squirted over the exit holes demonstrates the flow of water. Curiously enough, this internal water circulating system also serves a number of smaller animals that lodge themselves inside of sponges. These smaller animals use the sponge to supply them with a steady flow of water to bring them their oxygen, all with no effort on their part, of course. We might say these smaller animals are sponging on the sponge. This collection shows just a few of the animals that sponge on the sponge. A baby starfish, a small snail, marine worms, which often grow 2 or 3 feet in length. Over 1,400 such small animals have been found living inside just one sponge. We can trace one of the large central canals quite clearly from the top down in this sponge and get an idea of the intricate system of small canals feeding into it. Although sponges have various shapes, they all use a water circulating system to get their oxygen supply. This one, called a cake sponge, has only 1 or 2 large outlet holes at the top. This one has a vase-like shape, the point growing downward. This sponge simply pumps water through its walls from the outside to the inside. The sea anemone is a more complex animal than the sponge and is physically active to a limited extent. Yet it, too, gets its oxygen without benefit of special organs, simply by absorbing it out of the water through the skin of its hollow, tube-like body and waving tentacles. The jellyfish, a close relative of the anemone, gracefully waves an umbrella-like fringe up and down to force water through canals in its body and also to circulate water about its outside skin. An example of a still simpler skin-breathing animal is the marine bristle worm. But some worms enclose themselves in a hard tube for protection. Then less water can come in contact with the worm's body, so special apparatuses or movements must be developed to get oxygen. For example, this sabellid worm waves thread-like filaments around in open water to absorb oxygen. He also breathes partly through his skin, but since his body is encased in a tube buried in the sand, not enough water circulates over his body alone to supply all his oxygen needs. Among the starfishes are several curious examples of adaptation. In this hard cushion star, the skin, the tube-like feet, and other parts of the body all help in taking oxygen from the water. The tube feet can be pulled back into slits along the underside of each arm. Hard stone-like teeth along the slits protect the soft feet from attack. The cushion star lives on the bottom, where his flattish shape protects him from being turned over by the waves. The hard, blunt spines and tough skin discourage attacks from enemies. Each of the little feet ends in a suction cup for getting a good grip on the bottom. But another type of starfish has different problems. This star lives beneath the sand, coming out only to feed. Skin breathing is a problem for him because sand would interfere with free circulation of water over the skin. He solves the problem by a skin covering made of thousands of hard umbrella-like shields. They hold back the sand and let water flow freely over the skin itself. Each little shield is separate from the others, so the arm can still move freely. This starfish has 2 rows of long, pointed tube feet on the underside of each arm. Such skin-breathing animals as these move about very slowly, if at all. Movement uses up energy, which in turn uses up oxygen. These animals have such simple and relatively inefficient breathing methods that their energy level is low. Immense effort seems required by this starfish simply to turn itself over. The laborious movement becomes a kind of slow-motion ballet. Once the star is back in normal position, the tube feet take over and move it in a slow, gliding motion across the sand. Now here is a more complex and active animal, the horseshoe crab. To supply energy for moving his heavily armored body, he has developed a more efficient, specialized breathing apparatus, a kind of gill called a book lung. The soft-bodied octopus, whose hiding place we discover through a glass-bottom bucket, can move very energetically when he needs to escape an enemy in open water. Then he is jet-propelled by a stream of water pumped out of his body's sac. He produces this jet stream simply by breathing hard, so his movement through the water is merely a byproduct of his breathing action. When a protective shell completely encloses an animal, as in the case of the conch, a special extension of the shell conceals a breathing tube for pumping in the water. Most fish draw water in at the mouth and pump it out over efficient oxygen-absorbing gills, well illustrated by the moray eel. The all-important and delicately constructed gills of most fishes are protected by a hard, bony outer covering. Beneath this gill plate, the gills themselves are attached to these bony arches. The arches help protect the fragile gills from being torn by chunks of food as the fish swallows. The stingray has several interesting adaptations for living on the bottom of the sea. Enlarged side fins take the place of the flat, powerful tail of most swimmers. The ray roots in the sand for clams and other bottom animals. If he took in water for breathing through his mouth, he would of course suck in sand along with the water. So he has developed water intake holes on the top of his body, just behind the eyes. Gill slits on the underside near the mouth let the water out. Movement of this entire area does the pumping. Just in front of the mouth is located a sensitive smelling apparatus, for the ray must find his food by sense of smell. His eyes, being on top of his body, can keep on the lookout for enemies. So far, when we have mentioned breathing, we have been talking about a process which takes oxygen from water. All true underwater animals must be able to get their oxygen in this way. But a few marine animals, like the porpoise, do breathe oxygen directly. The porpoise is a mammal and has lungs instead of gills, just as we do. He exhales sharply and quickly gulps a lungful of fresh air as he rolls to the surface. Again, a hole in the top of the head is better adapted to this job than the mouth. The porpoise never accidentally breathes in water as well as air because an automatic flap closes the breathing hole if wetted. Thus, in a variety of ways, from the simple absorption of dissolved oxygen in the water directly through the skin and the lower forms of animal life, to the direct inhalation of air by mammals, the animals of the sea solve the problem of obtaining the oxygen essential for their survival. Each animal's method of breathing is adapted to his particular environment and his particular way of life. Another of the major problems of survival in the sea is to escape the many physical dangers of the environment. These fish, for example, died from loss of blood. Unusual turbulence in the water stirred up the bottom sand. Sharp sand grains in the water pumped continuously over the delicate gills had fatal results. These fish were simply not adapted to the problem of breathing water heavily laden with sand. Then there is the ever-present threat of natural enemies, the predators. An unsuspecting boxfish blundered into this octopus while the octopus was sitting for a portrait. Neither realized the situation for a few moments. Then the struggle for survival began. The victorious octopus may not find his prize very digestible for reasons we will point out later. The little sand flea hides in the sand to keep from being washed away and at the same time to escape the shore birds. The snapping shrimp, on the other hand, has to seek protection among the rocks. Animals living in the open, shallow flats may develop still another form of hiding, blending into the background by picking up bits of background material to conceal their outlines. Still others hide by using deceptive color patterns which can be changed to suit the background. Another form of protection is body armor, illustrated by the common edible conch, who searches the shallow grassy flats for food. When threatened, he can draw eyes, claw, and breathing tube into his shell, leaving no soft, edible parts exposed to an enemy. Even when traveling, by means of this single claw, he keeps well concealed beneath the shell. Some of the fishes, too, have body armor. The boxfish has thickened scales, which weld his body into a solid box. This might be an example of over-adaptation. In gaining protection, the boxfish has lost in alertness and swimming ability, as you saw when one blundered into the octopus. Some defenses have an offensive aspect, like the needle-sharp and poisonous spines of this sea urchin. A still more active defense weapon is the single sharp spine on the tail of the ray. Tiny teeth along the edges of this spine make it a particularly dangerous weapon when the ray slashes his tail about. The spiny projections of the rock lobster all point forward. This lets him back into rocky holes without being hung up by his own spines. Small fish of the coral reefs need speed and agility to avoid being dashed by the waves against sharp rocks and coral, as well as to escape enemies. These little fish are the natural prey of larger fish, such as jacks, who in turn are the prey of still larger fish. Even the striped moray eel, whose body is so well adapted to hiding in small holes and crevices, can put on a burst of speed when necessary. The common shrimp has a particularly deceptive backward movement obtained by flicks of the tail. His cousin, the rock lobster, uses a similar flicking motion of his powerful tail for quick getaway. Nothing looks more ungainly and slow-moving than the octopus oozing along the sand. In open water, when need arises, however, he can assume an almost perfect streamlined shape for quick escape. The rock lobster also has an ungainly shape that can be streamlined for rapid movement in the water, although in a backward direction. Using his spindly legs, he can move forward more slowly. This type of lobster has been recorded as migrating over 100 miles in a few weeks' time. As a third major problem of animal adaptation, let's consider the food problem. The really fundamental source of food in the sea is not the little fish that is eaten by the bigger fish, who in turn is eaten by a still bigger fish. The basic sources of food in the sea are plankton and detritus. Concentrated plankton looks like nothing much to the naked eye. Under magnification, however, the jelly-like plankton concentrate separates into many tiny individual organisms. These small plants and animals exist in vast quantities, but thinly distributed in the open sea. Plankton forms the entire source of food for many animals of the sea. So plankton feeders need a method of separating such tiny particles from the water. The sand flea does it with sticky, feather-like antennae. The barnacle has feathery legs with which to comb the water to filter out the plankton. The sponge uses his water circulating system to get plankton as well as to get oxygen. Microscopic hair-like structures inside the sponge's canals comb the plankton out of the water as it flows by. The clam sucks plankton-bearing water in through the lower tube and out through the upper, capturing the plankton on sticky surfaces inside the shell. Some of the jellyfish capture plankton with a similar flypaper arrangement of waving threads. The second basic source of food in the sea is detritus, the dead and decaying matter that ends up on the bottom of the sea and along the edges of the shore. Detritus consists of both animal and plant material. This material, through processes of decay and action of the waves, gets broken up into finer and finer particles. Some animals are especially adapted to browsing on detritus that falls to the bottom of the sea, as for example, this sea cucumber. Some of the fine detrital material gets thoroughly mixed with the sand. Another type of sea cucumber has adapted to this special problem of separating out the tiny food particles. Animals of this type eat sand along with the detrital material. Their digestive systems process the sand to screen out the food, returning the sand to the bottom, gradually building up these mounds. This is the sea cucumber that makes the mounds. He feeds head down in the sand, with the tail sticking up into the mound. These and other such animals can process as much as 500 tons of bottom mud and sand per square mile in the course of a year. One more major problem of adaptation, the problem of salinity. Seawater, of course, is always salty, but not always equally salty. A quart of it normally contains this much salt in solution. That's about 3.5% by weight. Animals have to adapt to this feature of the marine environment too. If the concentration of salt in the water changes from this proportion, the environment can become deadly. Here, for example, is a sea urchin in a pool left by the receding tide. A hard rain before the next tide may be fatal, causing the urchin to absorb more and more water as the solution inside its body seeks a balance with the water outside. Carried far enough, this can kill the sea urchin, paradoxically drowning him with too much water. The other extreme, evaporation from the tidal pool, can increase the saltiness of the water. In this case, the saltier water outside the sea urchin will seek to balance the two solutions until the sea urchin loses so much water he dies of thirst. This, then, is the kind of problem faced by animals living in the intertidal zone, that zone between the lowest and highest reaches of the tides. Constant changes in salinity here, caused by rain and by evaporation. At the lower edge of the intertidal zone lives the barnacle. His method of adapting to these changes is to seal himself off from the outside world. When conditions become unfavorable for survival, he simply plugs the hole in his shell from the inside with a special movable plate and waits for better conditions. Higher on the rocks in the spray zone, the periwinkle can also isolate himself from the environment temporarily. He closes off his shell with a window made of a mucus secretion. Even in the open water, where there is considerable runoff from heavy rains, the saltiness of the ocean can vary considerably. Most animals of this habitat can adapt by simply moving to another area. This sponge, however, could not retreat from the fresh water flowing into the sea from a nearby river, and so part of the sponge has died off. However, even the swimmers can't help swallowing some seawater with their food. Salt then passes through the walls of the digestive organs into the bloodstream and raises its salt content. Special glands in the gills remove this extra salt from the blood and put it back into the sea to restore the balance between the animal's internal and external environments.
This has been a brief survey of some of the major ways in which animals of the sea adapt to the conditions of life they encounter. You have seen a few, in fact very few, of the adaptive devices. These devices enable animals to overcome their particular survival problems. This is what ecology is all about, the relationship between the living organisms and their external environment, how they can obtain their vital supplies of oxygen and food under varying conditions, how they meet the perils of enemies, and the physical forces of nature. From observations of the interrelationships between the animal and his environment, we can see that the animal is truly a part of the area in which he lives. If we take the animal out of his area or ecological zone, not only does the animal have difficulty in adapting to new conditions, the very fact of him having been taken away from his natural habitat has also altered the ecological character of that habitat. In this sense, we can say that the organism and its environment are indeed parts of the same thing, an ecological unit.
This is National Educational Television.